So once we have our samples, how do we go back to a continuous time signal? We've suggested that this can be done as long as we've met the Nyquist sampling criteria. But what's the process? So the process we're going to use is very similar to what we used when we converted from continuous to discrete, in that it's going to involve impulse trains and then some operation. In this case, we take x of n and we convert it back into the impulse train form. So we want to get back to s, or xs of t that we had before. From there, we now have a continuous signal, and we can go back to our reconstructed signal. So I'm going to call that XR for reconstructed. There are a few problems with this that the astute might notice. The first is that XS, as we've talked about before, is impossible in real life. And this is an ideal low-pass filter. And an ideal low-pass filter has an impulse response that is the inverse DTFT, or the inverse Fourier transform, I guess in this case, of a box, which is going to be a sinc function, which is infinite in both directions. So also impossible in real life. So in reading technical papers, scholarly papers, it's not uncommon to see something like this, where the idea is developed, where maybe we assume that we know the probability of x, and based on that we can come up with some optimal solution. And once it's all developed, then it's revealed, and usually no surprise to anyone, that you don't have that quantity and you have to estimate it. But even so, the framework can be useful. It's the same way here. Sure, we can't do XS in real life. Sure, we don't have ideal low-pass filters, but at least we know what our goal is, and now we can try to approximate that as best we can. So, given that, let's see what XR is actually going to look like. We'd have XR t is going to be the convolution of xs of t. This is continuous time convolution, but the same properties of convolution still hold. It's just that it's done with an integral instead of with a summation. So, as you recall from, and if you don't, it's right up here in the upper right, xs is a sum of impulse responses. And since convolution is a linear operation, this expression for xr turns out to be sum over n of xn times, and now we have delta of t minus nt convolved with h LPF of t, and when we convolve something with a shifted delta, we just get a shifted response, and so we're going to get xn times h low pass filter of t minus nt. So in other words, we have taken our impulse response, that is our low pass filter HLPF, and looks like a sinc function. And we now replicate that same sinc function many times. Each time it's scaled by x of n, and shifted by t, and when we put it all together, we will get back our original signal. Well, given that ideal low-pass filters are hard to come by, we could use non-ideal low-pass filters. So, okay, I guess first I've magically copied in here an example of what reconstruction with the ideal low-pass filter might look like. You can see we have these arrows indicating x of 0, x of 1, which is now in the continuous time domain x of t, and so on and so forth. At each one of these, we have, whoops, there we are, we have a sync function that we have copied into there and added it up. Notice that the nulls of the sync land perfectly on the other samples. So each sample, when reconstructing, does not impact any of the other samples, but it does impact the area in between the other samples for all time. So here we have, whoops, I want to do that in green, another one, and its associated sync function. And all those add up to a very smooth function, which it's showing here is a dashed line that interpolates between. Now, it's interesting to note that this particular function does not, it's not smooth necessarily. It's smooth, but it's not monotonic or a simple curve in between the samples. And in this case, we actually have something that where the original waveform must have multiple frequencies, and it bounces around in between, and this perfect reconstruction picks up on that. Well, we could try another simple method, and that is to use a zero order hold circuit instead. So now we're coming down to how do we actually implement this in practice. And this is the easiest. Essentially, that gives us an H that looks like this. And in fact, we'll distinguish it from our other H's by calling it ZOH of t, where t is on that axis. And so what does this look like? Well, when we convolve this with a string of impulses, we are going to get something that looks rather blocky. So, not the best reconstruction. This would be X reconstruction of t. But it's fairly easy. Why is this easy? Because if you are doing a digital to analog converter, every time a sample comes, you set a voltage at the output. When the next sample comes, you change the voltage to the next sample. So electronically, this is quite easy to do. It just doesn't give results that are very smooth. Well, of course, this might be a particularly bad example. In practice, we might get something more like what we see here. I'll copy this onto the other page. So in this case, our reconstructed sample basically follows the contours. You could look at the squared off line and you could imagine that you see a sine wave that's just a little bit rough if you will, around the edges. Now, we would expect our reconstruction of a sine wave to have just one frequency. Obviously, with all these sharp edges, we're going to have more than one frequency. And so the reconstruction here has introduced additional frequencies that shouldn't be there. But that was a very simple method. Let's go ahead and look at some others that we could use. And we can already see it here, but just pretend like I haven't already ruined the surprise. Cut. And let's go ahead and try interpolation as another method of doing reconstruction. In that case, we have H, we'll call it int for interpolation filter. Interpolation can be done with a linear filter, and it just looks like this. T minus T1 time axis. There we are. So now when we use this, let's say we have some specific samples that we're trying to reconstruct. Put it here. There. That's enough to be getting on with. Since they're T apart, when we replicate this filter right there, we get one there, and we'll get one here, and then we'll get one here, and so on for the rest of the samples. But when we reconstruct, adding these two lines together will get us something right like that, and adding those two lines together gives us this. So we have now a linear interpolation between those, and we can see what this looks like on a larger scale. It certainly makes a waveform that looks much more pleasing than what we had with a zero order hold. So another option is a windowed sync function. Whoops. So a windowed sync function approximates the ideal because, as you might know, the sync function dies out at 1 over x. So it doesn't take too long before nothing much is there anymore. So if we did our sync function and we just tapered it nicely right down to 0 and left it right there, then we would have something that approximated our ideal reconstruction filter. And maybe we're a few % off, but it's very close. And so a windowed sync is actually a very common option to use for something like this. Indeed, if I were to reconstruct the above sinusoid with windowed sync, it would be at that resolution impossible to tell that it hadn't been a perfect reconstruction. And that's only windowing it to a few periods out. By going further, you can get even better results. Before we go on, let me mention one other approach that is commonly used. I'm just going to sketch it out as an outline for you. And that is, as I mentioned, it's very easy to use a zero order hold filter electronically. But the problem is you end up with spurious frequency components because of the sharp, jaggedy edges. Well, what if we actually had sampled it at such a rate that the output essentially looked like that with a zero order hold? In other words, it looked really good. Very few errors, or whatever was there was negligible. Well, this is, then when we reconstructed, there wouldn't be much problem. And just to make sure, we could put it through a regular low-pass filter to wipe out any spurious high-frequency noise that might have been introduced when switching between levels in the digital to analog converter. This is called an oversampled digital to analog converter, and it is almost universally used for things like audio. So we won't spend a lot of time talking about it now, but that's another option. I will say, though, that sometimes, especially when CDs were the way to listen to music before MP3s kind of took over, there are always advertisements on the package or on the label. If you'd go to the store, maybe to buy a CD player, and it would talk about an 8x oversampling converter. Well, what it essentially means is they can use very cheap electronics to do their digital to analog converter, because they do all the hard work in the digital domain. They take the original audio and they sample it to a higher rate so that now they can throw it out using a cheap, easy digital to analog converter, and then a very simple filter. And this simple filter just wipes out whatever is left of the high frequency components, leaving everything else okay. So it's not so much of an issue anymore. However, nearly all audio DACs use some form of oversampling to get higher quality at the output.